It was good. For the beginning of chapter 5, this is where we officially get into integrals. So I need it quiet, please. Officially into integrals. So just like before we started derivatives, we looked at the tangent problem and the velocity problem. So we looked at two applications of derivatives, not knowing what a derivative was yet. So this we're going to be going through the area problem today, and then the second problem that ties in with integrals is called the distance problem. So it's kind of two applications of what you would use integrals for without actually knowing yet how to find an integral or work with integrals. So just getting you to understand the idea. So there's a lot to go through, but it's just, again, building that sense of how to actually work through these and then also why you're working through it the way that you are. So for the first example, and we're going to come back to it later, this is the first example here. But it says, find the area of the region S that lies under the curve y equals f of x from A to B. So then I have included here more specifically, S is this region that is bounded by the graph of a continuous function f, where that function in this example is greater than or equal to 0. It's completely above the x-axis for the portion we're focused on. The vertical line's x equals a and x equals b, and then it's bounded on the bottom by the x-axis. And we are to find the area of that region. Yes. So then this is where I just want to get you thinking about what area actually means. So if you had to define area, how would you define area?
The amount of planar space
So you said the amount of planar space that something occupies. Okay, so I know you know, like if I asked you to find the area of a rectangle, I'm hoping you would know how to find the area of a rectangle. How about area of a circle? Thanks. Since I had to give some of you that on the test. You do need to know area of a circle. Just making sure, hey, you know it now, that's what counts. So the idea here is we know how to find the area of a square or a rectangle. You know how to find the area of a circle, of a triangle. If you had a polygon, you could break it into, say, different triangles, find the area of each triangle, add them all together, or break it into different shapes that you know how to find the area of. The problem with this example is we have a curve as one of our edges. How do you find the area when something is a curve? So how we're going to go about this, we're going on to a separate example. We'll come back to that one. But we are first approximating a region by using rectangles. So some of you I know have already spoken to me about this. You're kind of familiar with this process anyway. So it says, for example 2, so this is now a specific function, y equals x squared. It says use rectangles to estimate the area under the parabola y equals x squared from 0 to 1. So if we have, this is y equals x squared, zoomed in from 0 to 1, so this is the region S that we're looking at approximating. So one thing is if I drew a square around this region, what would the area of the square around that region be? 1, because it has a length and a width of 1. Okay, so therefore we know that the area of S, it must be greater than 0, but it also must be smaller than 1, because a square of area 1 fits around it. So area of S is somewhere between 0 and 1. We can conclude that here. Now, that's not a very specific estimation just to say, oh, it's somewhere between 0 and 1. I know between 0 and 1, that's a pretty small interval, but we can get a better estimation than that. So now what happens is we divide it into 4 strips. So we divide the interval 0 to 1 into fourths, so that each strip that we see here has a width of 1/4. And then we can turn these strips into rectangles one of 2 ways. So the first way we're going to turn them into rectangles is we're going to take the height of the rectangle to be, if you look at an interval, the height of the rightmost edge. So for this first one from 0 to 1/4, where I see where 1/4 is on that curve, I would go straight over to draw a rectangle there. And then I would do the same thing from 1/4 to 1/2. I would use the height at 1/2 to draw in a rectangle. So I'll finish drawing this in, and then if you want to look up here just to see how I'm drawing it. I'm making 4 rectangles, and the heights of the rectangles are at the right end points of each interval. And why I'm using rectangles is I know how to find the area of a rectangle. It's length times width. So then this gives then a picture. This is kind of the in-between. So then this, I actually have what it looks like. But now you're finding the area of these 4 rectangles and adding them all together to approximate what the area of S is. So it's not exact, it's an approximation. Let's just pick this first rectangle. I know that the area is length times width. I know the width of all of these rectangles is the same. It's 1/4 since I divided 0 to 1 into fourths. So I know the width is 1/4. What is the height, or how would I find the height of that rectangle, and then of each rectangle? Okay. Yes, so this height is, because I used the right end point, the 1/4, it's whatever the y value is when x is 1/4. And since the function is y equals x squared, the height is therefore 1/4 squared. Okay, so this first rectangle would be a width of 1/4 and a height of 1/4 squared. And therefore it would really be 1/4 cubed, or 1/64 would be the area of that first rectangle. The second rectangle would have a height of 1/2 squared. The third rectangle would have a height of 3/4 squared. And so it's because of how these were drawn. There is another way to draw them. Because we took so from 0 to 1/4, we took the height at 1/4 and drew it over to make our rectangle. The height is therefore the y value when x is 1/4. So then you're plugging 1/4 back into the function to get the y value. And so it's for the first rectangle, it's 1/4 squared. For the second rectangle, it was 1/2 squared, and so on. All right, so if I were to write this out, we're letting R sub 4 be the sum of the areas of these approximating rectangles. The R is because for each of the 4 intervals, we used the right end point to create the height of the rectangle. And the 4 is the number of rectangles we have, or the number of strips we divided it into. So I'm not going to write out the actual values. I'm writing out how to get the values. But that first rectangle, again, would have an area of 1/4 times 1/4 squared. Plus, the second rectangle still has a width of 1/4, but a height of 1/2 squared. The third rectangle still has a width of 1/4, but a height of 3/4 squared. And the last rectangle has a width of 1/4 and a height of 1 squared. But you would find those 4 areas, add them all together, and just to save some time, I have the value you would get. I rounded it to, let's see, I kept 5 decimal places actually. So this comes out to be approximately 0.46875, but this would just be calculated on your calculator. And this is the approximation we would get, again, for the area S under the curve from 0 to 1. So any questions? Again, need me to explain anything on how to get that value? And then I have a question for you. Would this be an overestimate or an underestimate? Overestimate. Why? Yes, you have, it's hard, I know I kind of already filled this in, but you're including all of this area that is inside of the rectangles, but not actually under the curve. Okay, so that would be an overestimate. Now, that doesn't mean right endpoints are always overestimates. It depends on the curve. So for this particular curve from 0 to 1, the right endpoints give you an overestimate. So then, rather than using right endpoints, we could have also approximated it using left endpoints. So that means we still have the same intervals, 0 to 1/4, 1/4 to 1/2, 1/2 to 3/4, 3/4 to 1. But now on that first interval, from 0 to 1/4, I'm going to use the height at 0 as the height of the rectangle, which then, since that function value is 0, there's really no rectangle even there. So this would be a height of 0 squared. The second rectangle then, so on the interval from 1/4 to 1/2, I would use the height at 1/4. So I'd have a height of 1/4 squared. The third rectangle from 1/2 to 3/4, I would use the height of 1/2 squared. And then the last rectangle would have a height at 3/4, so 3/4 squared. Yeah, so this one, for this curve, the left endpoints will be an underestimate because you can see the rectangles, there's area under the curve that's not included by the rectangles. So we're going to let L sub 4 be the sum of the areas of these approximating rectangles. Again, L for left endpoints 4 because we have 4 rectangles. So our first rectangle has a width of 1/4 and a height of 0 squared. Plus the second rectangle has a width of 1/4 and a height of 1/4 squared. The third rectangle has a width of 1/4 and a height of 1/2 squared. And the last rectangle has a width of 1/4 and a height of 3/4 squared. And so this, again, just to save time, you would type this in your calculator. I have the value for us already. So 5 decimal places, it's 0.21875. And this, as we had just said, would be an underestimate for this curve. Okay, so there's 2 ways you can get your approximating rectangles on an interval using the right endpoints or the left endpoints. Now, what is shown here is to get a better estimate. So we first looked at an estimate if you only had 1 rectangle. Then we went to 4 rectangles, which gave us a better estimate. We were from 0 to 1. Now we're from 0.21 something to 0.46875. If you keep increasing the number of rectangles you have, you will get a better and better estimate. So that's what is being shown here. This is showing the right endpoints on top, left endpoints on the bottom for 10 rectangles, 30 rectangles, 50 rectangles. And then this table also shows what the actual approximations are if you have 10, 20, 30, 50, 100, and 1,000 rectangles. So if you look at the approximations for left and right when you have 1,000 rectangles, what does it appear that the actual area might be? about 1/3, 0.3 repeating possibly, really close to 1/3. It actually is exactly 1/3. We will see later on how to get that. The idea here, though, is kind of going back to that idea of a limit. So as you increase n, the number of rectangles, then both the left and the right endpoint approximations become better and better approximations of the actual area. So that therefore we define the area A to be the limit of the sums of the areas of the approximating rectangles. So area would be the limit as n approaches infinity of the right or the left endpoints, which in this case, for this example, we're approximating based on what we know that it would be about 1/3. Now, will you actually have to take limits in this section? No. But you have to understand that what we are learning is a limit. It is a limiting value that we're finding. No. Right, but n is representing a number of rectangles. So it's not an actual x value on a curve. It's not saying what are the y values of the curve approaching, but what is the area approaching if you have an infinite number of rectangles. Yes, Connor?
I don't understand why you would do like 30 different rectangles when you put one of the four, just add the area of the triangle on the graph. There's like really close to like triangles.
For this curve. Right, and you won't have to by hand. So this is to get you to understand the idea. In some cases, you have to use rectangles, say if you don't actually know the equation for a function, but you have a table instead that you could set it up with. For the ones you'll be doing by hand, you would never be asked to do 50 rectangles by hand. So there are ways to get the exact values, not having to do this. But this is, you still have to understand what the value you're finding represents. Okay, so then back to example one, that really general region we had, now that we looked at a specific example. And I do want to say you do need to see the notation in this section. I don't want you to get hung up with the notation in this section. So understand the ideas behind it. So the region S we looked at the very beginning on the very first page. So the whole idea, whatever function you have from A to B, you start out by subdividing that region into n number of strips. And it should tell you in a problem to use 6 strips or use 3 strips. Let n be 5, something like that. And they're just calling those strips S sub 1, S sub 2, all the way through S sub n. And all of the strips have equal width. So I do want to say examples you'll work through, they do not have to have equal width. But if you're dividing them yourself, you'll probably divide them into strips of equal width. So then, the width of the interval from A to B. So how would you calculate the distance from A to B? Yes, but you don't need it. From A to B, other way around, B minus A. That's okay. That's all right then. All right, so the width of interval from A to B would just be B minus A. Therefore, if you divide B minus A into n strips, we call the width of every rectangle or every strip delta x. And it's B minus A divided by n. So you're taking your interval A to B and dividing it into n equal strips. N. All right, so then you would have, it says these strips divide the interval A to B into n sub-intervals. And I'm just going to list these out you'll see me go through an actual example too. So your intervals would be starting at A, which you could also call x sub 0, whatever your starting x value is. And that would go, I'm going off of what they have up here to x sub 1. And you would know what these values are once you figure out how far your width should be, what your delta x is. So you'd have x sub 0 to x sub 1, x sub 1 to x sub 2, so on and so on, all the way to x sub n minus 1 up to x sub n. Okay, so our intervals from the example we just did were 0 to 1/4, 1/4 to 1/2, 1/2 to 3/4, 3/4 to 1. Those are the 4 intervals we had in the previous example. And then it says the right-hand endpoints of the sub-intervals are. This is more so just to know how to come up with the endpoints. So if you're starting at x sub 0 to get whatever x sub 1 should be, you would add your delta x to it. So again, this is where I don't want you to get hung up in the notation. X sub 2, therefore, would be, if you're again starting with x sub 0, it would be adding 2 delta x's to it. X sub 3 would be adding 3 delta x's to your A value or x sub 0 value. But where this is leading, we can therefore approximate the area S by the sum of the areas of the rectangle. So again, R would be the right endpoints. So what I'm going to do here is circle these. If you have intervals written out, that means if I'm using right endpoints, my function values should be evaluated at the x values that are on the right end of each interval. So those are the x values that are determining the height of your rectangles. So your first rectangle, the height would be whatever your function evaluated at x sub 1 is, multiplied by the width, which is delta x. So this is coming up with a more general formula. The second rectangle would have a height of whatever f of x sub 2 is, multiplied by the width, which is delta x. And then added all the way up to the last rectangle would have a height of f of x sub n, multiplied by delta x. And I'll show, actually at the bottom, I'll explain the left endpoint. So again, notice the x sub 1, x sub 2, x sub n, those are the x values I had circled above. So this again is just showing as you increase n, you have a better approximation. So the formal definition is here. Area A of the region S that lies under the graph of the continuous function f is the limit of the sum of the areas of approximating rectangles. So it would be the limit as n approaches infinity of the right endpoints, which this is the, aside from the limit, this is the formula we just wrote above for r sub n. But again, you will not be taking limits. You just have to understand that it is a limit. But then it says you also get the same value if you use left endpoints. So I just want to point out how this is different here. If your intervals are what they were above, x sub 0 to x sub 1, x sub 1 to x sub 2, all the way through x sub n minus 1 to x sub n, the left endpoints means the left x values of each interval determine your heights. So notice the first rectangle has a height of f of x sub 0. The second rectangle has a height of f of x sub 1. The last rectangle has a height of f of x sub n minus 1. So the heights are different. And then there's still multiplied by delta x, which is the width. Okay? You'll usually be asked for one or the other. Or what I'm going to talk about quickly next, you could be asked for the midpoints instead of the left or right endpoints. All right, and then before we actually get to Another specific example of this, instead of using left or right endpoints, this is even more general. So you could take the height of, they call it the ith rectangle, to be the value of f at any number x sub I star in the ith subinterval. Again, notation, don't get hung up on it. All this means is, say you have the interval from x sub 0 to x sub 1. You don't have to use the left endpoint or the right endpoint. You could use any x value in that interval as the height of your rectangle. And that would just be called a sample point. So if you see the notation like x sub 1 star, that just means, or with the asterisk, that just means a sample point. And it doesn't have to be the end point. It could be any number in between. The most common choice for a sample point in an interval is the midpoint of the interval. So really the three that you're worrying about today are being able to find right, left endpoint approximations and midpoint approximations. So this is just an even more general case. So f of x sub 1 star could be the right endpoint, could be the left endpoint, could be any x value in that interval. So just more general. But again, that would be the area. And then I do want to get to the example, but this is the sigma notation. I'm not sure how much you worked with sigma notation leading up to this class. But the sigma symbol, what this means here, this would be a summation. It represents a sum. So this means for this expression, you start out by replacing the I in the expression with 1, and you plug in every value until you reach n. And then all of those values are added together. So it says after it what it actually means. If you plug 1 in for I, you would have f of x sub 1 delta x. Plus, then you would plug in 2 all the way up to n. So it's exactly what we were just writing out, but it's written as a summation, the sigma notation for it. So this is just the different sigma notations for this here would be right endpoints, because you're starting out with f of x sub 1, which would be the right endpoint of the first interval. This second one would be the left endpoints, because if you put 1 in for I, you have f of x sub 0, which would be the left endpoint of the first interval. And then this would be for any sample points. So it could be midpoint, the last one, because it has the asterisk. Yes, Connor. I is just a random variable, yeah. I'm not sure why they chose I. Okay. We may not get through all of example 3. That's okay. I just want to get you the idea. So example 3 says, estimate the area under the graph of f of x equals 25 minus x squared from x equals 0 to x equals 5 using 5 approximating rectangles and right endpoints. And then it does say to sketch the graph and the rectangles. So I actually want you to see how to work through this without graphing it first. The graph is so you understand the visual. You don't have to graph these in order to actually work through them though. So this is typically how I'll work through it. I first will find what my delta x is. What is the width of each of my strips? So my A value is 0. My B value is 5, and I'm using 5 approximating rectangles, which means n is 5. So if you use that formula for delta x, which is B minus A divided by n, you would have, yes, 5 minus 0 divided by 5. So each of your rectangles will have a width of 1. Then I find it helpful to actually write out what my intervals are. So my first interval, I'm starting with 0 and I have a width of 1. So my first interval goes from 0 to 1. Second one is from 1 to 2. Third is from 2 to 3. Fourth is from 3 to 4. Fifth is from 4 to 5. And however many intervals you should have should equal n. If I'm dividing it into 5 rectangles, I should have 5 intervals. So then if I'm using right endpoints for each interval, this is why I find it helpful to write out the intervals. The rightmost x value in each interval is the value that determines the height of my rectangle. So I would call this R sub 5, right endpoints, 5 rectangles. My first rectangle will have a height of f of 1 and then a width of delta x, which is 1. And yes, I'm going to need to know what f of 1 is. I'm just writing it out this way first. Plus, my second interval has a height of, using 2 as the x value, f of 2, and again a width of 1. Plus, third rectangle would have a height of f of 3 times 1. Fourth would have a height of f of 4 times 1. Fifth would have a height of f of 5 times 1. Okay, so I would calculate these values, add them together. They're all multiplied by 1, so just calculate these 5 function values, add them together to get your area. Based on the time we have, I just want you to see how to set up the other ones, so I'm going to just kind of do a fast forward here. This comes out to be 70. So you could go back, actually find the function values if you wanted to make sure that you can get 70. But are there questions on how that was set up? So that's how you would find it. It does say I know to sketch the graph and the rectangles. You don't need to, though, in order to actually calculate it. All right, so then I want to show you how this would be set up if you use left endpoints. So right endpoints, I circled up here in teal. Left endpoints, I would still have the same delta x. I still have the same intervals, but now the left x values in each interval determine the height of my rectangles. So this is how L sub 5 would be set up. Your first rectangle has a height of f of 0, and then times the width of 1. Plus the second rectangle has a height of f of 1 times 1. Third rectangle, height would be f of 2. Fourth rectangle, height is f of 3. Fifth rectangle, height is f of 4. So that is the difference, and why I think it's helpful to set up or actually write out the intervals so you can see which x values you should be plugging into your function. Okay, again, I'm going to fast forward. This comes out to be 95. Yes, this ends up being an underestimate. Really quickly, I know we're getting near the end here for midpoints. Just so you see how this is set up. This means the height, you still have the same intervals, the same delta x, but the height would be the midpoint of the first interval. So the midpoint of 0 to 1 is 0.5. Your first rectangle would have a height of f of 0.5. Second interval would have a height of f of 1.5 times 1. Third would be f of 2.5 times 1. Fourth would be f of 3.5 times 1. And last would be f of 4.5. Okay, and that would come out to be 83.75. So I would say it's the setting up That is the more challenging part, knowing how to set it up. Otherwise, it's finding all the values in your calculator, so it's more tedious than anything.
So what is,
Sorry if